and start. So we stay on schedule. So my name is Janine Cook. I'm here to introduce our session today about everything Proxy apps. We're going to talk some about platform and application readiness, and then some about what we hope to and anticipate to do in the future. So I am not David Richards. I'm really sad to say that he stepped down from leading this project, and so I am trying to take over for Dave, which we all miss him a lot, probably mostly me included. All right. Okay, I'm not forwarding. There we go. Okay, so this is a really big project. Most of you probably know this, but it spans several labs, and we also have some university contracts. A lot of people are involved, 6 labs and 2 universities. So it's been a pretty big, really fun actually, and good to get to know everybody project. Truly a team effort and a cross-lab effort. So our primary goals are really twofold: to curate and release a Proxy app suite that represents the ECP application complex. And we do that on a yearly cadence so that we can, track changes in the application space. And, we've said that the suite has to be easy to use so that the community will adopt it. And I think we've done a fair job of that. It's pretty easy to grab and install. And I do think that many people actually within DOE and outside DOE are using the suite to do various research. So we also are charged with assessing the fidelity of these Proxy apps compared to their parents to ensure that we really should be using them and we can use them accurately and safely as a co-design mechanism. Co-design, and acquisition mechanism. And I think we've also made some good progress in that area. What we've accomplished to date, quite a bit. This is the 3rd year of the project. Well, we've completed 3 years. I guess we're in our 4th, I think. But we've actually, done quite a bit of work. So on the curation side, we've released the 4th version of the ECP Proxy app suite. It's there for your use. There's lots of documentation up there. We also released the ML Proxy app suite as part of version 4 as well. So, there's Vinay will be talking about this later in the session, but there's a suite of about 5 or 6 ML Proxy apps that you might be interested in. We have a catalog of 75 plus Proxy apps that are categorized by programming model and language, so they're easy to sort of sift through. I really encourage you to go look at that. And then we also have SPAC packages so that, they're easier to build and easier to port. So take advantage of that, please, if they can be of use to you. So we've done a lot on the quantitative assessment side. We developed an assessment methodology to quantify the fidelity of a Proxy compared to a parent. That's really based on ML similarity algorithms, done a lot of work in that space. Quantified predictability of parent performance based on Proxy execution time. So how predictable are those proxies of the parent execution time, looking at scaling studies. We assess the fidelity of key kernels compared to the respective parent key kernels. And then a lot of work has been done in the IO side on Maxio. They validated it and extended it to include capability to model IO for AMR codes. And as you all know, IO is kind of a big problem. So the other area that we've really concentrated on is trying to fill in gaps and needs in the Proxy app space. Argonne has done a large portion of this work. And as you can see, there's a lot of new Proxy apps that have been developed in the last year and are available. And we're still doing some development, hopefully in the future. So, please look for these coming online. Some of them I think are, but we're working on incorporating these into the suite proper. So we'll be doing some of that work in this next 2 quarters. So please go look at the reports and the papers at our main Proxy App Suite site if you get a chance to do that. They're all up there and available. All right, so the future. Basically, we want to, maybe encompass some more science domains in the next Proxy App Suite, and also make sure that we have really good coverage across GPU implementations, especially since the systems are sort of diverging with respect to programming model or language for GPUs. It'd be nice to make sure we have good coverage there. We are going to continue to support continuous integration and usability of these suites. We're going to do a quantitative assessment of ML proxies. ML proxies are a different beast. The data might be, it is a little more important there. So we're going to be working on, hopefully in the future, trying to figure out how we do that. We're also hopefully going to be doing some model-based I/O, developing a model-based I/O proxy to model exascale I/O behavior. That'll be coming out of Oak Ridge based on their prior work. And develop scientific application workflow proxies as well. Workflows are becoming more and more important, and we don't know a whole lot about linkages and hardware requirements and things of that nature. So we're going to hopefully try to make an impact there. Also, I think there's a lot of work that we propose to do in the follow-on, if we get it, are to develop methods that support development of more representative proxy apps. So this is interesting work in kind of maybe helping applications teams not have the full responsibility of developing the proxy, but have some support in doing that. So maybe some templates, some first order models, some things that they can maybe start with, and then glue pieces in if they need them, but giving them a little bit more support so that they don't have to develop the whole proxy on their own if they don't have to. So we're also looking at some further development of new proxies. We're going to test some of the proxies that you saw on the prior slide that have been developed recently with some of the newly developed ECP library capabilities on some of the systems. As we all know, the systems are getting closer to being here with Frontier coming soon. And so this team is really looking at testing performance and capability wise some of the libraries and things that have been developed through the ECP project to date. And also we're looking at developing the FFTX library further, which is essentially, a new exascale FFT library that's going to be more robust so that it can support more applications that use FFTs in just a better way. So with that, I just want to say we have some good talks. Our first session is going to be on the proxy app development, sort of in the application readiness space. And then our second set of talks will be on the ML suite and sort of what we have going in that area. So with that, I'm happy to take questions maybe after this whole session. I want to make sure the speakers have plenty of time. So with that, I think we're going to switch to Sawmill. So I am going to stop sharing and let you share.
All right, thanks, Jenny. Can everyone hear me? I'm hoping that's a yes. Okay. All right, I'm going to start the presentation. How does that look? Can you guys see my screen?
Yes.
Okay, great. All right. So hello, everyone. My name is Somal Patel. I'm a computational scientist working with Ramesh Balakrishnan on the Proxy Apps project here at A&L. So specifically, I'm working on the IMEX LB Proxy app, which is a lattice Boltzmann-based app for solving CFD problems on GPUs. I just want to acknowledge our collaborators from the City College of New York in particular, PhD student Chunheng Zhao, and now postdoc at ANL Gang Lu, who did a lot of the legwork for this effort. So the objective for this effort is to develop an open source self-contained CFD code suite with minimal dependencies capable of running on heterogeneous HPC platforms like those with GPUs. So in addition, we do aim to augment the DOE's portfolio by utilizing the lattice Boltzmann method to develop a highly scalable and portable code for solving single and multi-phase flow problems. And finally, we like to take our proxy app and characterize features like compute patterns, memory movement, communication overhead to understand and project performance on current and future vendor hardware. So just a bit of a background on LBM or the lattice Boltzmann method. It's unlike traditional CFD methods, which solve conservation equations like the macroscopic properties, such as mass, momentum, and energy. In fact, LBM is not solving the Navier-Stokes equations. It's based on discrete particle kinetics governed by the Boltzmann equation. And for those of you that might know, it also has deep roots in lattice cellular automata. And so there was a lot of work done there in the 90s by Fritz Hassliger and Pomo and actually the mid 80s on that work. And so here in this equation at the top, F represents a single particle probability distribution function, and omega is a term to describe the effects of the collisions between those particles. Now, for continuum flows with the low Knudsen number, the equation can be discretized into special velocity sets, leading to a set of first order hyperbolic PDEs called the discrete Boltzmann equations. So the velocity sets can come in a variety of configurations shown here in the lower right-hand side of this box. And they come in a variety of flavors for 2D and 3D problems. And it's worth noting that the velocities shown here as vector E alpha are predefined for a given configuration. So if we take the discrete Boltzmann equation and discretize that along the characteristics of space and time, we get the following lattice Boltzmann equation shown here at the top. The left-hand side conveys the material motion of the particle, while the right-hand side uses the well-known BGK approximation for the collision term. And there's other approximations there. I just show the BGK approximation here as it's commonly used by many practitioners. So here the big F represents a body force, for example, gravity that acts on the system. And so in practice, the equation is solved via a two-step procedure where fictitious particles undergo a collision step followed by a propagation or streaming step. And the streaming step is akin to solving a linear advection subproblem with a CFL number equal to 1. So from a software point of view, there is no interpolation or extrapolation used in the streaming step. It enjoys the simplicity of moving or copying data around memory, and this is due to the uniform regular grid that is commonly employed. The macroscopic variables are then recovered by taking the zeroth and first order moments, for example, to recover density and momentum, from which you get the velocity. And it's been shown that via using multi-scale expansion procedure called the Chapman-Enskog procedure, one may recover the Navier-Stokes equations that I write here. Now, I write them in a compressible form here because there is a low Mach number assumption baked into the scheme, and so that's commonly used in implementations of the lattice Boltzmann equation. So how does this all relate to what we're trying to do with the proxy application? To enable the schemas on the GPUs, we've developed our proxy app to come in two different flavors. One is the Fortran flavor on the left, and the other is in the C++, which is what we're currently working on in the current fiscal year. As a first step, we tackled the development of both on ALCF's data GPU, where we can use the OpenMP programming model as well as the Cocos portability layer to offload hot kernels. And in both cases, MPI is being used to enable internode communication. We also employ domain decomposition to scale our problems up. And at the moment, the Fortran code can tackle single and two-phase flow. And in particular, we are able to implement the two-phase flow models, which can capture an interface, such as, for example, between a gas and a liquid. And I should say that we can even do binary liquids, so liquid-liquid interaction, for example, oil and water. Now, moving on, what we've done so far in terms of scientific benchmarks is validate and verify tests for both codes on benchmark single phase flow problems. In particular, we investigated flow past a cylinder and past a sphere. The top two animations showed vorticity for the flow past a sphere. In addition to verifying relevant features like drag coefficient, we also compared how flow field data generated with the device, for example, the GPU, against data that was generated on the host. And for velocity and pressure, these differences were on the order of 10 to the minus 16, so almost the same. We're also validating some two-phase flow results for droplet coalescence, liquid water into ambient gas phase as an example. This simulation at the bottom right makes use of a well-known interface capturing model whose implementation was relatively easy, as it appears only in a local pointwise collision, in the local pointwise collision step of the LBM. And so it's this particular coalescent problem is a common test to assess the stability of the model for two-phase problems and multi-phase problems. So we also dug into the performance of the code. We started by looking at some of the hottest kernels. It's well known in the LBM that collision can represent a significant portion of the runtime. So this slide is just showing two different implementations of the collision kernel for the Fortran and C versions. The left shows our use of the OpenMP target teams distribute directives around a do loop, which calculates the updated distribution function for all fluid grid points. And the right uses the parallel forward dispatch, which in Cocos, which takes the index ranges for each Cartesian direction to enable concurrent calculation of the updated distribution function. And at the moment, we are planning to isolate this kernel and create, let's say, a sub benchmark repo to assess some optimization strategies for it. Finally, we looked at scaling and application performance. The results in these plots show intranode strong scaling results on Theta GPU for the Cocos enabled version. The results are for 3D flow past a sphere. The image on the left plots the figure of merit known as megalattice updates per second versus the ranks for a problem size of about, this problem was around 10 million grid points. I should note that we are binding one rank to one host device pair. So in this case, we do see a speed up or performance gain of roughly 2x when utilizing the GPUs. The image on the right shows a similar plot, but this time we're plotting average wall time per time step versus total problem size as measured by the grid points we're using. In particular, we're seeing strong scaling is exhibited across 3 different problem sizes. So in summary, I just want to say that we are on track to develop the LB-based CFD code suite with minimal dependencies to be scalable on the upcoming heterogeneous HPC platforms. And so I'm including some references to the repos that we created along with a report for the work that's been done. And so next steps that we want to do is get a little bit deeper into the performance of our work, perform some roofline analysis to better understand bottlenecks, for these hot kernels, including the aforementioned collision kernel. We also want to do additional development and validation for some of the multi-phase problems that's another level of complexity that we want to get right. And we're also planning to develop native DPC++ SQL and CUDA implementations of the code. And I think this would lead to, like a better performance comparison across different programming models employed with the code. And ultimately, we want to determine best practices for the hot kernels and perhaps fine tune them for a given architecture. So with that, I'll conclude the talk. I think I'm over 10 minutes. Apologize for that. Thanks for your attention, and I'll take any questions.
Okay, I don't see any questions in the chat. So I guess if there are no questions, we will move on to our next speaker. Alvaro.
Hey, hello. 1 second. Let me see if everything is fine. Can you see my screen?
I can see it.
Perfect. So I have 5 extra minutes, right, from Samuel. I'm just kidding.
No, we are running a little early, but.
Okay. Well, first of all, thank you for inviting me to give the talk. It's a pity. It's still a pity that we cannot meet in person, but I hope this is different in the future. Anyway, I'm glad to be here. So I want to present you some advances of what I've been developing since almost 1 year ago with a new mini proxy app called MiniGap. So my background is chemistry, and I'm working in chemistry and materials. So I'm influenced by that, right? So I want to first acknowledge Argonne, DOE, and obviously the ECP funding, and also acknowledge my collaborators who really helped me to do this job. So the first one is Shan Stafford, a PhD student who did most of the work, and also Murat, who is one of my partners and colleagues at Argonne, and Jose, who is from Michigan, and he gave really good insights of where to go. So I think the motivation of why we have proxy apps was covered in the beginning of the session, but basically I will just summarize that these mini apps are self-contained pieces of software that solve some representative problem in computational science, and is small enough that other projects might learn from the practices used in these codes, and probably these codes could help to educate or be as a reference for future developments. And well, it's clear that this is needed to the very diverse architectures that we will have in the exascale era that is practically now, right? So it's not just not that dream. Is in few months we will have access to these complex systems, right? So, and all these systems have different vendors, and obviously different kind of accelerators and programming models that will challenge the current developers. Yeah. So in machine learning, in my view, we are trying to solve complex equations, but based on empirical observations, right? So some equations are very complex to solve, or very complex to encode or write or type in a code. So machine learning comes to help to learn from data points, try to reveal the complex patterns and get an approximated equation. So one of the equations that are very important in chemistry and physics is the Schrödinger equation, which is difficult to solve because this is the first equation you can see. I don't know if you can see my mouse, but so this is Eigen problem, right? So we don't know, the problem in this equation is that we don't know the Hamiltonian, which is this H with hat. The psi, we don't know the psi. We don't know the E, and we don't know the psi, right? So, and R are the positions of the atoms. So this is very difficult, right? So even if we can propose a form of the Hamiltonian, then we have to fit the psi function to guess the energy. So the energy is unobservable, right? So this equation is sometimes solved iteratively. So we propose, so we define a Hamiltonian, and then we propose a psi, and we get an energy, and then we modify the psi, and we compare the new psi with the old one based in the energy, right? So this is a way to solve it, and actually so this kind of problem currently uses more than 2/3 of the computational time in supercomputers in DOE, right? So this is an atomistic model to evaluate the properties of materials. Anyway, so so in this project, in the Minigap, I tried to solve this equation, or not to solve this equation, so try to find a way to fit this function, so that the function of the energy, in this case, the property is the energy, and the structure is this R, the capital R. So I tried to find a way to fit a function with machine learning using a Gaussian process. So I focus, so most of the materials machine learning projects, they all these steps. So you produce reference data, you collect the data, then you produce a model, you validate the model, and then you go to your application. I'm going to focus only in the model. And the model I use here is the Gaussian approximation potential, which is based on Gaussian processes. And the idea is to create a descriptor for atoms, so which will help to produce, to predict an energy per atom. And this is really nice because then it's size extensive, so you can train over few atoms and then apply for over thousands of atoms. So actually, we use this to study materials. For instance, the phase transition of hafnia. So we train over 96 atoms, and we managed to do simulations over using this model over systems of 700 and 6,000 atoms with almost the same precision as the methods we use the quantum mechanical methods we use for the 96 atoms. And actually, this was really nice because what you want is to have models that are very close to what you have in the real life, right? So in the real life we have thousands or millions of atoms. So, and when your model is this size, I mean, you can compare easily with experiments. So the Gaussian process is, as I told you, is basically what you do is you fit a function using Gaussian functions, and this is using a Bayesian principles, and it's not parametric, so it's not biased by any. It's not like a linear regression where you bias to have a line. So in this case, it's completely no parametric. And basically, what you do is you create. So you take data points and then you compare those data points, forming a covariance matrix. And then what you do is you invert that matrix and you get the coefficients from the Gaussian functions. So I think one of the most difficult parts here is creating this covariance matrix, how you compare two objects. And the second part is solving the equation, diagonalizing the covariance matrix. And then obviously it's also expensive when you predict, because once you have the coefficients of the Gaussian functions, you want to apply this several times. I mean, you have thousands of atoms, you have to apply this thousands of times, right? So this is the other part that is complex. So one is comparing the objects, solving the equation, and predicting. So in this case, K is the covariance matrix, and obviously, yes, I forgot to mention. So the beauty of the Gaussian process is that the noise that you have in your method comes from the data, right? So you're not inducing a noise like you do in kernel-rich regression methods. Yeah, so again, the covariance matrix is how you compare objects, and this is a complex step because there is not a single way to do that. There are multiple approaches, right? So you can create your own, and even so here I'm showing three of the most common families, and even in these equations you can see hyperparameters like sigma or d or lambda that or sigma that you don't know beforehand, so you can also have a leeway to, I mean, you can also optimize these hyperparameters. So one of the very popular, of the most popular descriptors nowadays in machine learning the atomic potential is the SOAP descriptor, or the smooth overlap atomic position, where you define the environment of the atoms like densities. So it has a radial contribution and an angular contribution. So you expand this density in terms of polynomial. And then what you do is you compare this density in the environment of the rest of the atoms, right? So what you get is for each atom in the training data set, you get some coefficients, and then what you do is to compare them, you just do the dot product, right? So this is similar to one of the kernels we saw here, the polynomial, right? So this is one of the approaches. So we created Minigap, which solves the Gaussian process problem, using a SOAP descriptor. We solve the Gaussian process in a single node using GPUs or CPUs. Most of the ML acceleration relies on TensorFlow, which is very flexible, and also you can easily move from CPU to GPU. So that TensorFlow really helps to have a portable code. So we work in the descriptor, in which are written in C++. So we added OpenMP to make use of multi CPU and GPU. Also, we have two approaches. So one using the full Gaussian process prediction, and also the sparse Gaussian process, where you just take the most representative points. So you have to do an extra step, just taking the most representative points from the database to create the model. So again, so it's a Python code which calls TensorFlow, and also in-house C++ code. We have an interface with Jupyter, which make it very easy to visualize the results. And even if this is a small code, I think is good as a test, and also might help to other complex codes to, for instance, study high parameter optimization, right? So because the solution is quite fast. So this is a very small set of example of code, how this looks like when you do mini-gap prediction. So you call to the settings, you define a data set, you split your data set in training and testing, you define a kernel, and then you produce the model using the data, right? And then you can predict properties. So this is a very high level example. So in this case, I'm going to show some validation experiments. So we took a data set of alkali alcohol, and what we did is we took different conformations of the same molecule. So we changed the bonds and the angles of the molecule. So we always use the same 3 carbon atoms, 1 oxygen and hydrogens. This is difficult, right? Because if you move slightly the atoms, the change in the energies is also very, very extremely small. So this I think was a good test, and you can see here the evaluation of the energy. So the predicted ML predicted against the true energy, and I think the regression is very acceptable. Also, we tried this with a data set with molecules with different sizes of atoms. So with 3 atoms, 5 atoms, 10 atoms. So it's different to this because it's the same size. So this is diverse in size, and this data set has 7,000 chemical compounds. And we train over 3,000 structures. And what you see in this plot is we are just testing over 10,000, over 1,000. So performance-wise, obviously this is a tricky plot. I'm computing here the time to the solution and prediction of the Gaussian model using CPU, which is in blue. And the orange and yellow is in a GPU, right? It's a P100 and a B100 card. Obviously, I think it's not fair because I'm just using one processor here. So the solution is like several orders of magnitude. You see, this is logarithm base 2. But anyway, so I think, yes, so you can see, so I'm just demonstrating how this code works in different architectures, right? Regardless of if the compression is fair, still I see improvements when I compare GPU against an old GPU with a new GPU card. Yeah. So anyway, this is a John code. I mean, it has things to. There's a lot of room of improvement in the code, and we're working on that. We also are improving the descriptor generation, and these descriptors also will help us to apply, for instance, deep learning. So you can do not only Gaussian process with the descriptors, but also so deep learning, and that will be also an extra mini app in our plans. Well, thank you so much. I hope this was of your interest. I know there is a lot of chemistry and physics, but yes, thank you for your attention. I think I passed my time already. Sorry.
Okay. If there's any questions, I think you'll have an opportunity to ask after the next talk. How's that? Thanks, Alvaro. All right. So next up is Ramesh.
Hello all, are you able to see my title slide?
I see it.
Okay, you see it, great. Okay, my name is Ramesh Balakrishnan. I'm a computational scientist at Argonne National Lab, and I'm going to be presenting work which my former postdoc, Youngdae Kim, actually did in generating a proxy app. So the whole idea behind this proxy app was to essentially have a self-contained code which can solve a complete scientific problem. And in this particular case, the problem that we've actually chosen is that of forced isotropic turbulence in compressible flows. So you don't need any large or complex grids for this. The grid that is used for the computations can be generated by the code. And we essentially decided that we'll look at the porting aspects of this particular code. And for this particular problem, when we start doing these computations on the GPUs. So Youngdae Kim, as I mentioned, is my postdoc who actually did this work. This work was initially the CPU version of this code called HiPAR was developed by Debjyoti Ghosh, when he was a postdoc here at Argonne, and now he's at Lawrence Livermore Labs. And Emil Constantinescu in MCS was one of the advisors of Debjyoti Ghosh when he did his work over here. Okay, so why is it called HiPAR? So we're a little bit ambitious. So we basically wanted to come up with a proxy app that can be used for solving PDEs, which have both the hyperbolic as well as the parabolic components in them. So what I essentially mean is if you look at the Navier-Stokes equation and you write it in this form, du dt is equal to the advective terms plus the viscous terms plus any source term. It turns out that the advective terms are hyperbolic in nature, the viscous terms are parabolic in nature, and then you have the source terms. So what we do is we follow the traditional route of finite volume methods, where we focused on the hyperbolic terms or the convective terms and how we essentially use the Wiener scheme for this. So this is the standard formulation over here. I'm not sure if you're able to see my cursor, but the second box over here, the second line basically shows how we discretize the equation and how we essentially represent the fluxes in the walls. Now, in a Wiener scheme, you essentially make up a scheme which is higher order, and the way you make up the scheme is by using a convex combination of lower order schemes. So in our particular case, we decided that we wanted to use the fifth order Wiener scheme, because despite the fact that there are higher order Wiener schemes like the seventh order, and so the fifth order is based on our experience is sufficient to actually do a pretty good DNS of compressible flows. So we decided that we would do a fifth order Wiener scheme. And a fifth order Wiener scheme is basically built up of three third order Wiener schemes on adjacent nodes over here, as shown in this figure. And in order to compute that, we essentially use a central Wiener scheme for all the interior points. When we get to the edges or the boundaries, we essentially use an upwind biased Wiener scheme, which is the same order. And so the task over here is to first calculate the Wiener weights, the optimal Wiener weights, and then basically use these optimal Wiener weights to calculate what the interpolated flux is. So there is no data dependency between grid points and the computations. So the same instructions can be used on all the data points. And so this is a perfect candidate for parallelization on GPUs. So what we actually did was our strategy to accelerate high power on GPUs was essentially based on three key implementation principles. So one first thing is that we wanted to go for what is called a lexicographic thread configuration. So the way we actually do this is, and I'll show you more of the details later, is to basically make sure that each grid point is basically assigned to a thread, and the order in which these grid points are assigned to the various threads is basically in a lexicographic order. I know I've repeated the same word. What it means, I'll show up. I'll show in the next slide. We wanted a GPU-only data pipeline. So what this means is that we didn't want to transfer just the compute-intensive parts of the code, which is what everybody follows now, onto the GPU. And we wanted to basically have all our computations on the GPU so that effectively we use the CPU just to launch the kernels. And finally, when we write out the output. And we wanted to go for what is called coalesced memory access, which is a fancy way of basically saying that instead of having an array of structures, we decided to use a structure of arrays. And very quickly, you can note over here that using these, we were actually able to obtain, when we compared the performance on one GPU core to one CPU core, we essentially were able to see more than about 200 times the speed up for this. So the lexicographic thread configuration is shown as follows. So if you were to basically consider this to be your arrangement of threads, and by the way, this is an initial experiment, which we, when we initially developed the code, we decided that we would do it all in CUDA. Currently, we have a COCOS implementation of this, which is actually running on one of the precursor platforms that we have in-house, which will later become Aurora. But because of NDA limitations, we chose not to show that. We are essentially focusing just on the CUDA implementation for this presentation over here. So if you look at it, you basically have all these various grid points. So essentially what we do is we take all these grid points, which are in a 2D or a 3D representation. Over here, we essentially map it onto a single 1D array, and we essentially map those points from the array onto the threads over here. And when we do this, we actually see that this simple rearrangement gives us about a 1.3 times improvement. When we use the tiling as it was in the code, as it was, we found that we take about 0.48 seconds per time step. And when we actually go for lexicographic ordering, take about 0.36 seconds. And so the basic idea over here is to make the thread IDX the same as the lexicographic order of the grid points. The next thing we did was we essentially decided that we would do all the computations on the GPU. So the basic way which we do this is to transfer the initial data from the CPU to the GPU, all the essential data. When we launch the kernel, we keep doing the computations on the GPU, and we get back to the CPU only when we transfer the final solution and any intermediate steps that we require. with regard to essentially making sure that we are essentially advancing at the same time step. So when we actually do this, and so initially when we found that we just decided to offload just the compute intensive part of the code to the GPU, we found that our performance was pretty bad. So we were essentially, the data transfer itself took about 272 milliseconds. And when we essentially decided to do all the computations on the GPUs, it is significantly faster when there is just minimal data transfer between CPU and GPU. So that accounted for another speed up. And then finally, we decided that we'd actually do the coalesced memory access, which is just, so the point to note over here is that every grid point, there are 5 variables. And so if you were to essentially say 8 bytes per variable, the initial array of structures, organization of the data structures that we had basically shows that you essentially have a 40-byte stride. And once we basically decided to make a modification in our data structures to use this structure of arrays, we brought that down to an 8-byte stride. So that accounted for another 3x improvement in the performance. Okay, so we went ahead with this particular, having made these changes and having noted these improvements, we decided to do a full-fledged simulation of forced isotropic turbulence, and we basically increased the number of grid points from 256 cube all the way up to a 640 cube. The idea was to basically saturate the GPU over here. And you noticed over here that if you take a look at the speed up on the left-hand side, we find that we basically tend to saturate about 512 GPUs on a 256 cube grid. And if you look at the weak scaling up to 64 GPUs that we did for a 640 cube grid, we noticed that our efficiency initially, when we just had 64 cube grids per grid point on 64 GPUs, our parallel efficiency is less than, maybe it's about 0.55%, or about 55%. When we increased it to about 128 cube, it improved slightly. And finally, when we did the 640 cube, it went up substantially more. So that's essentially where we are. We've essentially pushed this code out. We encourage people to actually download this code and try it out and let us know if you have any questions. We are currently working on the COCOS implementation of this on Aurora. And we have also almost completed a COCOS implementation of this on Summit. So we are going to be actually publishing these results of the work that we have done. And that's all the details I have now. So if you have any questions, do let me know. Thank you.
Thanks, Ramesh. And thanks, everybody, for the talks in that session. So are there any questions from people in the audience?
Janine, this is Kevin Huck. I have a quick question for the proxy apps in general. What's the status of the SPAC packages to install them? Because for those of us who aren't as experienced with some of them, SPAC is the easiest way for us to build those apps to test with them. And my most recent attempts with it weren't very successful. I'm just curious if there's any efforts to bring those up to date or make sure it includes all the most recent apps that are in the full catalog on the website.
Yeah, that's a good question. And I'm actually going to defer to Robert if I can. Robert, can I defer to you to answer that? He's one of the 2 people who works on that effort in particular. See if he answers. If he doesn't, I'll answer the question, Kevin.
I saw you
So,
unmuted, but I didn't hear, can't hear anything, so.
yeah, I think Robert's still muted. Maybe he stepped away or something. So in answer to your question, Kevin, is we realize that some things are out of date, and it's really, so this is what's hard is things change quickly.
Yep.
Right?
No, I understand that it's a big effort, and that's what I was just wondering if
Yeah.
if there are any resources being directed towards it.
So we are trying to fix the problem. So we are trying to direct some resources. So, to be honest, Los Alamos has 2 people who do this effort. And so it's a pretty big effort distributed among not very many people. And we are planning on putting, some pretty good effort into it into the next 6 months to get everything sort of unbroken before the release. But we've discussed this repeatedly about how we stay on top of this, and it's just a really hard problem. So, what I can say is that we are putting effort this next 6 months. So stand by. I know, I don't think you have to wait for 6 months, but I do think that because we have a release coming up, we do a new release at the end of every FY. So I think, we're going to revisit things that are broken, try to update those packages, and try to get, things working again. It's a hard problem, and we really need probably more people to work on it and keep these things up to date.
Sorry, I was just walking to the restroom. I think I was supposed to answer a question.
Yeah, Kevin had asked about, thanks, Robert. Kevin had asked about the status of the SPAC packages.
Okay, at a high level, we are working with the code teams to improve their SPAC packages. Once SPAC changed to Klingo, that became much more urgent because the Klingo concretizer will cause anything that's a broken package and dependency to fail. I think at this point we've fixed all of them, but there are still updates. For example, I think GCC 11 changed the default state for a lot of flags, and that breaks a lot of builds. So we are working to go through there and identify changes that need to be made, and working with the code teams to get those upstream if needed.
Thanks, I appreciate it.
Yeah, that's a really important effort. It's just a hard one to keep up with. Thanks, Robert. So are there any other questions for the 3 speakers who just spoke? So I guess I have one question for Alvaro. Alvaro, is Minigap available yet? And is it in a GitHub repo somewhere?
Yes, it is, but I did a major change because the first version, the 0.0.1 beta, was not cute. So I deleted like thousands of lines, and the reason is because my student was learning, right? So the student who wrote the most of the parts that I showed today, he was learning. I don't blame him. He's very good, but I needed, once he left, I had to put my hands on the code. So I have to push the new changes. But yes, it's in my Git repo. Yeah, Alvaro VM/minigap. I will soon update it, but it's almost done. Yeah.
Okay, so you do have it somewhere. If you do have it somewhere, can you just put that in the chat?
Yeah. Yes.
Okay. Hey, thanks. Appreciate that. Okay. Let's see. Are there any more questions? Okay, so here's a question in the chat for Ramesh. You showed restructuring the arrays in one of your slides. Was that done through low-level change, or were you able to use Cocos or some other abstraction?
That's a good question. So currently what I showed was what we have actually done with CUDA. We are still working through some of those very aspects with COCOs. And one thing that I forgot to mention, I guess, was that my postdoc Young Day, who was actually doing this work, he got a job offer and he left us. So he had to leave us fairly quickly. So we are essentially going to be working on this. And if you're interested, I can keep you posted on that. Thanks for the question.
Okay, thanks, Ramesh. Okay, so why don't we queue up the next speaker? We actually have a few minutes slush time. If anybody wants to go take a bio break, I would suggest now is a good time. And we're gonna be queuing up the ML talks about the proxies that are in the ML suite now. So Vinay, I would, maybe give it a couple minutes if people want to grab a cup of coffee, grab a beverage, do whatever. I'd say, start in 3 or 4 minutes or something.
Yeah, I'll just, share my screen and make sure things are working correctly. Okay, hopefully people can hear me and also see my slides.
I can hear you and I can see your slides.
Perfect,
I'm
thank you.
probably gonna go grab a quick glass of water. Okay. Renee, why don't you go ahead and start?
All right. So good afternoon, everyone. My name is Vinay. I'm a scientist at the Los Alamos National Lab. And this is going to be a high-level talk about the machine learning proxy application suite. Let me see. Okay. To give you an outline of the talk, I'll start by introducing why we are moving towards a separate suite for machine learning proxy apps and how machine learning proxies differ from traditional proxies. Next, I'll talk about the principles of machine learning proxy app suite and what qualifies to be a machine learning proxy application. With this, I'll briefly go through the ML proxies that we currently have in the suite and how they adhere to the principles and cover the breadth of machine learning space. And I'll conclude with a summary. So about 77% of the total data in the world was created in the last 5 years. So essentially, we have an explosion of data on our hands. This requires development of advanced techniques to understand all this data. And ML is at the forefront of technologies used to process vast amounts of data. And we have seen the use of machine learning techniques in practically every field of computing. It is being used for diverse applications, ranging from classification to control to recommendation systems. The HPC research community has also adapted machine learning for developing new simulation workflows, and also not only that, accelerating existing simulation workflows, HPC workflows that we have. Machine learning is also being used for optimizing resource allocation, and they're being integrated into job schedulers. So the purpose of machine learning proxy app suite is to collect proxy apps for understanding the impact of machine learning on scientific computing and how machine learning can be applied to problems of interest in DOE. So machine learning applied to DOE science has unique characteristics and can differ from typical applications of machine learning, such as classification of images or recommendation systems that are typically used in industries. So capturing these requirements in the suite will help represent machine learning workloads for hardware software co-design, benchmarking, and also algorithmic exploration. So with all these things in mind, we laid out certain principles of the machine learning proxy app suite. So first of all, let's define what a proxy app is. Let's go back to the basics. So proxy apps are models that capture important features of large applications, such as performance critical kernels or different programming models, communication patterns, etc. So in HPC modeling and simulation, this basically translates to simplified applications that are representative of large production codes. However, machine learning applications require a somewhat different approach. Typically, machine learning applications are data-centric as opposed to algorithm-centric. So, to give you an example, the same deep learning model can be trained with different data sets to perform different tasks. So, you're applying the same algorithm, but performing different tasks because you trained the model with different data sets. So for our deep learning models, sometimes it is essential to simplify the data sets itself while developing a machine learning proxy, rather than simplifying the algorithm or capturing some performance critical kernel. So we kept these things in mind while developing machine learning proxy apps. Machine learning proxies also differ from traditional proxies in other important ways. Usually, machine learning workloads rely on a complex set of third-party libraries, which are, this is in contrast to the principle of simple-to-build proxies. If you have ever written a machine learning application, then you probably have used third-party APIs such as PyTorch or TensorFlow, Keras, or for distributed deep learning, something like Harvard. But if you go ask data scientists not to use these third-party libraries for development of whatever they're doing, then it is almost impractical. So we have to think slightly out of the box and think of novel ways to manage dependencies. So essentially, what I'm trying to say is dependencies are unavoidable in machine learning space, but thankfully we have tools such as SPAC that are making it easier to manage dependencies. So if memory serves right, I believe there are more than 200 plus Python SPAC packages available already, and all the proxy apps that we have in the machine learning suite has SPAC packages already available. And the other thing that we have to keep in mind is, over the last decade or so, we have seen, an explosion in development of machine learning algorithms and techniques. So there's a rapid pace of innovation and discovery in machine learning. So good proxy apps that we develop must be nimble enough to adapt to such changes. So I'm not saying that the proxy app should remain constant and it should not evolve with the pace of innovation. All I'm saying is we have to build proxies, machine learning proxy apps by keeping the future in mind, as in we should be able to develop on top of what we already have and adapt the existing proxies to new innovations and discoveries. The intent of selecting machine learning proxy apps is based on two sets of criteria. The first thing is the suite must embody the core purposes and uses of proxy apps. Those are hardware and software co-design. For example, proxy apps are I would say one of the foremost uses of a proxy app is hardware software co-design, because proxy apps are used to work with vendors to improve upon existing and upcoming hardware architectures and also programming models. So programming model exploration and innovation is also one of the important features, features that is being used to develop by making use of proxy apps. Proxy apps are also used for development of numerical methods and algorithms that is, instead of developing or dealing with an entire complex application, we can take a subset of the application and maybe try a different way, a different parallelization strategy or an algorithm or a numerical method, and we can develop these new techniques by making use of proxy apps. And proxy apps are used for optimization and benchmarking, how different programming models perform, how the same proxy app performs on different hardware architectures, etc. And last but not the least, proxy apps are an educational tool. And we have to keep that in mind while developing a proxy application. Second, since we are developing a machine learning proxy app suite, the suite must cover the breadth of machine learning application space. So in machine learning, broadly speaking, we can categorize it into three parts. Those are supervised learning, unsupervised learning, and reinforcement learning. So the goal of machine learning proxy app suite is to develop proxy apps that represent different paradigms and cover different areas of research in DOE, such as classification, regression, detection, etc. Not only that, we want the proxy apps to encompass different neural network architectures associated with such paradigms. There are different architectures such as DNN or generative adversarial networks, variational autoencoders, etc. And along with this, the proxy apps have to be independent. That is, we want to provide standard data sets for inference and training along with the proxy app. So if the data set is not available, we at least provide data generators along with the proxy app itself, so that it is self-contained. So with these things in mind, we have selected and curated the following list of machine learning proxies. So currently we have Candle benchmarks, which is derived from the cancer distributed learning environment. We have generative adversarial network proxy called MiniGAN. We also have a reinforcement learning proxy called MiniRL. And we have proxy applications that does inference in hydrodynamic simulations called Cradle. We also have proxy apps that are derived from cosmology applications and also climate segmentation benchmark called MLPerf DeepCam. So in the next few slides, I'll go through each and every individual proxy that we have in the machine learning proxy app suite and do a brief dive into what each one does. Candle benchmarks were developed as part of the Cancer Moonshot Initiative, and it's a partnership between the Department of Energy, the National Cancer Institute, NCI, and the National Institutes of Health, or NIH. So the idea behind developing Candle benchmark is to get a better understanding of the disease itself. So essentially what Candle benchmarks do is they make use of all the cancer-related data, and they effectively build predictive models to provide guidance and support decisions on anticipated effective treatments for individuals. For example, if someone wants to undergo targeted therapy, then not much data is available on it. By making use of such predictive models as what Candle provides, it is possible to come to informed decisions. So Candle provides different, Candle addresses different problems at different molecular scales by making use of different deep neural network architectures. And specifically, it addresses the problems at molecular, cellular, and also population scales. And you'll hear more about Candle benchmarks in the subsequent talk by Jamal. Next, we have Minigan, which is a generative adversarial network proxy app, or popularly known as GANs, and is developed as part of the XLearn project. So GANs are deep neural networks that simultaneously train two models. So GANs typically consist of a generator and a discriminator. The job of the generator is to produce increasingly accurate synthetic data, whether they are images or music notes or something else. And the job of the discriminator is to attempt to distinguish between the synthetic data from the original data. So at the end of the day, as the training progresses, the generator becomes increasingly accurate, and it can produce more and more accurate synthetic data, and the discriminator also becomes smart enough to distinguish between this improved or increasingly accurate synthetic data from the original data. So Minigan aims to be a proxy app for multiple applications. In cosmology, Minigan is a proxy for Cosmoflow and Hexagan. They both use generative adversarial networks. And in a wind energy application, there's the Hexawind project, which also makes use of generative adversarial networks. And Minigan aims to be a proxy for all these applications. It is built using PyTorch and Harvard, and is used to generate plausible 2D and 3D maps, and the discriminator can be used to identify fake maps. So that is Minigan. Next, we have MiniRL. MiniRL is a reinforcement learning proxy app derived from the easily extendable architecture for reinforcement learning, or XRL, and is developed by the XLearn control team. MiniRL is used for control and optimization of applications and experiments. So this is different from traditional industrial or academic use of reinforcement learning. The feature, one of the feature of MiniRL that distinguishes it from other reinforcement learning techniques is that it has modular agents, environments, and workflows. So in the sense that it is useful for data scientists that want to develop new reinforcement learning algorithms. They can focus on agents. And if a subject matter expert wants to focus on an experiment or an application that they want to control, they can focus on the environments. And if a computer scientist working in HPC domain, they can focus on the workflows, which is essentially the interaction between agents and the environments. So Minigan uses a synthetic environment of cardpool with an added complexity of computing the value of pi in a distributed fashion. So this is a completely synthetic environment, and it uses the DQN agent and an asynchronous workflow. So this is MiniRL. Next, we have Cradle. Cradle stands for Concurrent Relaxation Through Accelerated Deep Learning. So Cradle performs inference with a trained machine learning algorithm on mesh geometry data from hydrodynamic simulations. It models the workflows in hydrodynamic simulations as if manual relaxation strategies were replaced with inline inference. Many options and optimizations are available in Cradle. One can tweak batch size, GPU, and also perform GPU optimizations for apply GPU optimizations for PyTorch, use different parallelization strategies, etc. And with this, timing information is provided for loading the machine learning model and also mesh quality metrics onto the accelerator. So, what's the time taken to load the model from the host memory to the device memory, and also for performing inference on the accelerator. So in addition, the metrics also indicate whether the model's computational cost can be hidden. So it provides all this information and makes it easy for people to see if machine learning can be an alternative, for manual relaxation strategies in hydrodynamic simulations. The next machine learning proxy app that we have is the Cosmoflow benchmark. So this is an implementation of the Cosmoflow 3D convolutional neural network. And this is written in TensorFlow Keras and uses Harvard for distributed training. So in this benchmark, deep learning is used to determine the physical model that describes our universe, and it aims to process very large 3D cosmology data sets for prediction of 3 cosmological parameters. There are various optimizations that has been performed for this benchmark. That is, it uses MKLGNN primitives for implementation of 3D convolutional neural networks, and also the Craze ML plugin is used for efficient scaling of deep learning using MPI. So with all the performance improvements, it enables processing of very large 3D dark matter distribution in the universe, and the 3 cosmological parameters that it predicts is predicted with unprecedented accuracy. So it is on par with any HPC simulation that is being run. Next, we have MLPerf DeepCam. So this is a PyTorch implementation of the climate segmentation benchmark and is based on the exascale deep learning for climate analytics code base. So as people may know, climate change poses a major threat to humanity and costs billions of dollars in damage. In fact, we in Los Alamos have a fire alert, and we all have packed our bags to evacuate just in case anything happens. So climate change is real, and it poses a major threat. So to alleviate all these problems, climate scientists have to run high fidelity simulations under different climate change scenarios for predictions. And this produces terabytes of data, and it is almost impossible or impractical to visualize all this data and do manual segmentation. Segmentation in a sense, doing pixel level classification on the images that you get from the simulations. So DeepCam replaces this manual segmentation with deep learning methods to extract high quality pixel level segmentation for different weather patterns, or to identify different weather patterns. And it makes use of state-of-the-art Tiramisu and DeepLab V3 architectures to solve the segmentation problem. Various optimization has been enabled on this benchmark, and it has been shown to scale up to 27,360 GPUs so far. Right, so just to summarize everything, we identified how machine learning proxies are different from traditional proxies, because machine learning proxies take a data-centric approach as opposed to an algorithm-centric one. So based on this principle, we laid out different principles of machine learning proxy suite, that is the ML proxy suite. Our proxy apps must embody the core purposes and uses of proxy apps, and also cover the breadth of machine learning space. And I also briefly discussed the different machine learning proxy apps that we currently have in the suite. And so far, we have used these machine learning proxy apps to test status and operations coverage of TensorFlow on the upcoming hardware architectures, both the early access, frontier, and GLSE systems. Right, that's all I have. Thanks for your attention. So are there any questions? I don't see any questions in the chat either.
So I may have a question or two.
Sure, Jenny.
So I guess I'll preface this with, I am not an ML person. I was many moons ago when ML was so much more impractical to do because of computational issues. But looking at this proxy suite, what I have a hard time figuring out is the linkages between the ML proxy that does some, performs some specific type of algorithm and the larger application. Now, I think on some of them it's pretty clear, right? But on some of them it's not that clear. And so how do we make those linkages? And some of those linkages are just through the data set, right?
Right.
So, a different data set might actually be applicable to a different larger application. So how do we do that, like as a user?
I think the onus is on the developers of the proxy app rather than the user. Just to reiterate or go back through the proxy apps that we have in the suite. Maybe one of the best examples is Minigan. Even though Minigan is a proxy app for cosmology applications and wind energy applications, essentially it is using a generative adversarial network. And what Minigan does is it takes the Sandia, the Thunderbird logo, the eagle looking picture, and it tries to generate an image of that, and tries to fool the discriminator, and the discriminator has to decide between whether it's a generated image or an actual image. So it's a very simple example, but all generative adversarial networks are doing is essentially a generator trying to generate a data and a discriminator trying to discriminate. So it covers the principles of what a GAN is doing, but in a very simplified fashion. I don't know if that answered your question.
Yeah, it does. And I guess one more question, if I can, is so from your perspective, what's missing out of this suite of proxy applications? Or does it, I know this field, this area is changing all the time. The application space is big.
Yeah.
What's missing, and how do we determine what's missing if there are missing algorithms?
The proxy apps that I covered in my presentation were in the 1.0 release of the machine learning proxy apps, and what we did in this version of the proxy suite is we wanted to cover as many different machine learning algorithms as possible. So we have proxy apps that does deep learning, both training and inference, convolutional neural networks, GANs, reinforcement learning, segmentation using 3D convolutional neural networks, etc. But in recent days, there have been, the natural language processing machine learning is gaining traction, and we should look at adding maybe a transformer model or something like that into the proxy app suite. And I think that is in the works because Candle is making use of transformer models for one of their benchmarks, and we are in the process of identifying proxies like that, and including as many or a broad range of machine learning proxies into the suite.
Okay, thanks for that. Are there any more questions from participants? Okay, then let's move on to hear. This is the last presentation in this session from Jamal on the Candle benchmarks.
Hi, can you hear me?
Yes.
Okay, so as advertised, I'll be presenting a little bit on the Candle benchmarks. The work is a collaboration with a lot of people, but I will present that. I'll give you the list of developers at the end. This is part of this DOE NCI partnership to advance exascale development to cancer research. It's a multi-year collaboration between DOE and National Cancer Institute and National Institute of Health. I'll give you a brief overview of Candle, which is, as Vinay said, the cancer distributed learning environment. I'll talk about the 3 pilots, which comprise Candle, and I'll give you some examples of the types of benchmarks that we've encapsulated in there. And I'll talk a little bit after that about the broader Candle stack and its relation to this package called Supervisor, which enables us to run at scale on the DOE machines. I'll show you some examples of the workflows that we can enable with that and how it's useful for sort of developing the workflows that we care about and improving the models and the data structures. And then I'll give you a brief wrap up with a status and some acknowledgements. And so the original goal of Candle was to develop this at-scale deep learning environment for cancer. At the time, we were originally building on these various open source deep learning frameworks, which have changed drastically in the last 5 years. And so, back when we started, Keras, had TensorFlow and MXNet and other things that probably people who are younger than us haven't heard of, but have died and gone by the wayside. And so there was a need to try to evaluate even which of these frameworks was the most suitable. There was optimization. There was the goal of optimizing all of these platforms for the exascale HPC platforms, and as part of that, of course, the proxy apps serve as a way to track the performance of the implementations of all of these frameworks on those platforms. The larger goal was to support the deep learning needs of the DOE and the NCI cancer pilots, which I'll get to next, and to provide this collaboration between the DOE, the HPC vendors, ECP co-design, and software projects. And the overall statement was this rather grand one, and enable the most challenging deep learning problems to run on the most capable supercomputers. But we've, as you see, we've managed to achieve that to some degree. And so the scope of Candle was basically to bring together these three main aspects that I think Vinay touched on. There's three different scales. So there's trying to understand drug response for cancer trials through machine learning. This RAS pathway, which is actually a coupling of machine learning with extremely large-scale HPC simulations. And then the treatment strategy, which by and large is a natural language processing problem, trying to analyze the cancer reports and textual data that comes in from pathology centers, and then to provide, use machine learning to automate some of that workflow and improve the quality of that workflow. And as I said, currently mostly natural language, but we'll be adding other types of data as we move forward. So Pilot 1, and recently they've renamed everything. So Pilot 1 is now IMPROVE, which stands for Innovative Methodologies for New Data for Predictive Oncology Model Evaluation. I'm not sure how that acronym actually works, but regardless, it's a broad suite of models targeting predicting drug response. And so this is taking data at the cellular and the drug response level. So you have drug descriptors, you have molecular descriptors, you have molecular features of tumor cells, and some of the examples here we have something simple like compressing the expression profile into a low-dimensional vector to make it more amenable to analysis, simple classifiers for classifying cancer type, predicting growth rates, and so this is essentially a drug efficacy given, and you can get quite complicated because you have multiple cell lines, you have multiple drug concentration and combinations, and multiple orderings in clinical trials. And given all those, can you predict which is the optimal outcome? And this, of course, is, if for those of you who don't know, based on the patient's genetic signatures, the drug signatures, the dosages that have been prescribed, and the order in which the drugs are used, the outcomes can vary quite significantly, and there are linkages between different drugs and toxicity levels, which are dependent on the patient's own genealogy. So this is quite a complex space. The NT3 is a normal tumor classifier. So given an expression profile, is it a normal tissue or cancerous tissue? And again, this UNO is one of the larger Pilot 1 benchmarks that's trying to predict tumor dose response that I just described across multiple data sources. One of the things I'll note about this is that these benchmarks have quite a varied runtime. So P1B1 runs in a few seconds. And so it's very amenable to something like newer hardware where you can't run an emulator for months at a time. And so you want to get a relatively small and easily testable benchmark. UNO takes several hours or days, even on a large machine. So we have a good range here, and as I'll talk about later, all of these are easily modified to change the amount of data and the runtimes. Admiral, there we go, is as I said before, this coupling of simulation with machine learning. And so this is coming out of Lawrence Livermore, and they are running extremely large detailed simulations of these lipid membranes And they're using machine learning to essentially try, in the simplest possible terms, to try to understand when something interesting is going to happen. So this is sort of a rare event simulation. You're trying to encapsulate characteristics of small patches of this lipid membrane and trying to understand when you can accelerate the simulation and skip over large time steps when you can infer that nothing interesting is going to happen. That was the original goal. And again, the improvement of the understanding of these RAS activation cycles and how these are done. There is only one benchmark in the pilot 2 section, but it's a fairly large one, and again relies on a huge amount of data, which are these time series coming out of these extremely large simulations being done on the leadership class machines there. Pilot 3 is Mosaic, which is modeling outcomes of surveillance data and scalable artificial intelligence for cancer, and this is the one that I'm working most closely with. As Vinay mentioned, we do have, in fact, a transformer model, P3B9, but it uses a small data set for a benchmark, but of course there are much larger data sets we can throw at it. The one that's being P3B1, P3B2 are these biomedical text classifiers. And in fact, P3B4 is one that I didn't show here, but it's actually the closest version of an API that is currently being deployed at the nationwide across various cancer registries to automate cancer report classification. This is a job that is currently assigned to people called registrars, and they have to scan a report and within less than a minute assign a correct cancer value, a correct value to several values of interest. And the goal is to develop a way to automate that and take several thousand man hours out of the loop and improve the accuracy levels at the same time. So this is just to give you a flavor of the kind of work that's being done there. And as I mentioned, we expect to roll out the transformer-based benchmarks, which are amenable to require large scale and actually very interesting when coupled to things like flex flow, which gives us better ways to parallelize the benchmarks. Briefly, the Candle software stack. And so the benchmarks themselves, the scripting level, these then target the lower level things like TensorFlow, LBAN, FlexFlow, which are the sort of the frameworks that are really what we're testing when we're running on this new hardware. And those, of course, as you well know, rely on these architecture-specific optimization layers. The layer that sits above this is this layer called supervisor, which allows you to do all of these higher level workflows. And the way this works is that part of the way the benchmarks were written is to use a bunch of functionality in the Candle library that I worked on with a bunch of other people. And the point of these is essentially to enable you to perform simple experiments in the command line, which then is coupled to these higher level scripting languages. And it's supervisor itself allows you to modularly plug in things like hyperparameter optimization or different data workflows to perform a whole series of experiments. I'll show you some examples later. So the Candle library itself includes a lot of utilities to simplify the commonly used workflows. And the idea is if you're trying to build a machine learning benchmark or proxy app, a lot of the time you end up just writing the same chunks of code or very similar chunks of code. And so we have simple utilities to fetch and validate data files, including model files, which are saved at MODAC, which is an NCI run data repository for models. We have noise injection models for testing robustness, data pre-processing, feature selection and data transformation. I'll talk a little bit about that later. Automated checkpointing so that if your job times out, you hopefully progress somewhere and got a good checkpoint out of it. Various UQ methods, including this abstaining classifier, which was developed as part of this work with the NCI and improves accuracy. Some heteroscedastic regression models. something called DARTS, which is a differentiable architecture search, which allows you to, a lot of the time, if you look at the way these models are written, they seem to be fairly ad hoc. You pick a model architecture that seems to work, and you play with it a little bit. And DARTS allows you to perform some more rigorous search in the architecture space to figure out if you have an optimal network topology or not. We have new stuff coming down the pipe, explainability methods. As you can imagine, if you're going to make predictions about precision medicine and deciding what treatments to give to patients, it would be nice to know what the features that model is predicated on, and whether those make sense to doctors or other professionals in the field. We're doing things with Smiles transformations. There's some very interesting work with methods that drastically improve performance of classifiers by transforming the data from text-based to image-based and things like this. Those are those image generators, which can generate image from drug descriptors. The integration here, this is just another sketch of this, the hyperparameter search, uncertainty quantification, training data analysis. I'll show you a workflow. And so the blue are the ones that we target. So the applications are the benchmarks, and these top level are the supervisor, various supervisor workflows. Here's a simple example of robust noise injection, and we just take a single noise data set and add a bunch of noise to it at different levels, run them all in parallel, and you can see in the plot right there that the performance of the model drops off as the noise level increases. Not particularly surprising, but there are ways to improve this performance actually with the abstaining classifier, which I don't think I'll show on this particular talk. Here's an example of hyperparameter optimization. And so you can, during the course of a run, various things like the size of the individual layers of the network, the learning rates, maybe the loss functions, and you can perform sweeps over these. This, I think, was done with an R-based optimization package that, again, could be modularly plugged in, and you can see the evolution of the loss goes from fairly bad to significantly better. We get forward as a magnitude improvement over some of these evaluations. And these will run, obviously, on a large HPC, I think, summit on several hundred nodes. Here's an incremental learning workflow where you try to infer which data sets are anomalous, and so you can train it on some data sets and then progressively refine the leave-out set. And what you can do is stochastically vary this and find which data sets are anomalous and which ones perturb the model training the most. I think that's all we have. And so those are just some of the examples of the things you can do. And these, again, are the large-scale workflows of the proxy apps, which also stress networks and other aspects of the workflow. So current status of the benchmarks, version 0.5 will be released the end of this month. We'll split out the Candle library so that people can use it more easily, because it's, even though it was designed for this cancer-based stuff, there's most of the stuff with the functionality we put into it has by design been more generic, and so like the noise workflows and stuff are being used for other things. Since ECP is winding down, benchmarks version 1.0 and Candle lib 1.0 will be targeted for a year from now, essentially. And we're hoping to spend a lot of time improving usability, because as with anything, these things evolve, and you realize how badly you did when you started. Those are the code itself and the documentation on github.io on GitHub. And I'll take any questions now, and I'll leave you with this list of the current contributors to the code. Thanks.
Thanks, Jamal, for a really good talk on Candle. That was interesting. Any questions? Please unmute if you have a question, or put it in the chat. So I certainly have some questions, Jamal. Okay, let me go. Maybe somebody else will pipe up in a minute. Let me go ahead. Can I ask you a question about Admiral? So,
Sure.
okay,
I'll do
so
my
you,
best, so.
yeah, I mean, I don't know much about the candle benchmarks at all. I clearly need to learn more about them. Because I think they would be useful for some of the other work that we're doing. So you said Admiral base, it's really meant their goal was to sift through the data and sort of be able to pick out where interesting things are happening, right? So were they able to do that?
So I think the person you really need to talk to about that is Brian Van Essen at Lawrence Livermore.
Oh, okay.
Yeah.
If I can jump in on that, the answer is we've had mixed success with that, where in the pilot 2 part originally, which preceded Admiral, we were able to we're using data-driven models, not the ones shown here, to find interesting patches and queue them up and score them for where we do the coarse grain simulation. We've developed the model you saw in the candle benchmarks, and now also a transformer-based version where we're looking at the sequence of frames as we go by, either individually with the current model, but we also have a transformer one that looks ahead to predict when a state transition would occur and provide a score to the interestingness of the frame. So that work is being done in conjunction with the pilot 2 team. Admiral is the follow-on where they're looking at adding not just coarse grain and fine and continuous simulation, but a macro modeling in between as well. And so the work's going to continue in that context. I hope that helps a bit.
Yeah, it helps a lot. Do you have any references? Have you guys written some papers on this?
There have been papers on the pilot 2 in general. On the candle specific models, we're still trying to get those put out in the community.
Okay. All right. Yeah, I would love to read something from this pilot 2 team. I don't know if you could maybe email me a reference. Would that be possible?
Yes, I can.
Oh, thank you so much. That sounds great. So I just had one other question. So Jamal, I know you mentioned Summit and I think Theta. So what other systems have, do candle benchmarks actually run on? Have you ported them to?
Well, they're being run on all of things. We have Crusher,
Okay.
Bach, Summit.
Okay.
I'm not sure what the status is, and Articus. So I'm looking at the number of Slack channels I have, and we have Slack channels for all of those. So those are all either being worked on or have been run. And realistically, this is one of these things where a lot of this really is just a way to something to test, TensorFlow or PyTorch or whatever the underlying framework is. It's really a test of the of whether that hardware has really reasonably good implementations of those packages. There is the flex flow angle, which is Legion based, and then there is since Brian is on LBAN, which is I think C compiled code, especially written to be parallel performant in a similar way to the way Legion is. And so those are apart from those two backends, everything else we're testing on these machines is really just what's the state of the TensorFlow, or what's the state of the PyTorch implementation, and how badly would it fall off a cliff at scale or something like that.
So I don't know if you can answer this question, but can you tell me out of the systems that you listed, which you're having the best luck on with respect to TensorFlow and PyTorch not falling off a cliff?
I cannot. I can tell you that even
Okay.
on something relatively mature like Summit, scaling of using something like Harvard, which is a pretty standard way to parallelize data drops off a cliff at a single node level. And when we compared that to FlexFlow, we were able to scale it out to 768 GPUs, which is 128 nodes without problems. So there are significant benefits to using methods that are much more aware and targeted, at scale. I'm not sure what the observation has been generally, that that scale for most of these machine learning backends isn't really as big as you'd like it to be. How's that? How politically correct that can be? So.
Yeah, I hear you. Okay.
So Janine, I just want to mention that FlexFlow version of the Candle benchmark is in the works, and we will be including it in the machine learning proxy app suite.
Right. I knew
And that should be based on PCB9, I think. So.
Okay. Yeah, that sounds good. No, very interesting. All right. Does anybody else have any other questions? Wow. I guess silence is golden. I don't know. So I think, well, if there's no more questions or discussion, I would call it a wrap. Thanks for everybody attending. We appreciate the time, and let us know if you have any questions when you're trying to get the proxy suite. Please let us know if you have problems, like Kevin's SPAC problem. It helps if you just send an email, so that even if we know we have the problem, we know that people want the problem fixed, and that helps us to prioritize a little better. So
yeah, I'll just reiterate that, Janine. There was a question about the Vino high power proxy app. So if people should feel free to download it. It's on Bitbucket. Hopefully we'll be able to get it onto the ECP proxy app suite soon, so that it has wider visibility. If there are any questions, they should shoot me an email, and I'll be happy to discuss that with them, or any of the other proxy apps, any of the Argonne proxy apps too.
yeah, thanks, Ramesh. We're all really willing to help and answer questions. So please use us as a resource, or just a way to get things done that you need to get done. If we can affect that in any way, we're happy to do that. So, okay, anything from anybody else? All right, well, enjoy the rest of your day. Thank you so much for everybody who spoke. The talks were awesome. I really appreciate it.
Thanks, Janine. Thanks everyone.
Thanks, Brian, for saving me on that question. So.
No problem, Jamal. Glad I could. Ginny, I guess, one thing I missed, I should say, LM is also designed to scale to thousands of GPUs on some of these problems as well.
Okay.
And has been demonstrated on several of the applications.
Okay.
Yeah.
Well, that's awesome.
I just didn't have the numbers for that, so I wasn't. That's all.
Yeah, I need to pay a little more attention to this ML space. Not only because I'm leading the Proxy app project now, but also because I'm finding myself getting a little into that space, right? Again, not that I really want to, but it turns out that it's the solution to some problems that I'm having. So I appreciate all the help and insight. I do, and thanks for answering those questions, Brian. I might ping you. Don't be surprised if I ping you.
That'd be fantastic. I'd love to talk.
Okay, that sounds great. Thank you so much. All right, thanks everybody. Have a great rest of the meeting. I'll see you in some sessions, I'm sure.
Great, thank you.
Thanks, Janine.
Thank
Thanks
you.
for organizing. Really appreciate it.